In exploring vector calculus, we would first ask the question, how does a vector change? And so we explore that idea through something called a position vector and a displacement vector. So what the position vector does is tells us where a coordinate point is in three-dimensional space, and we can do things with that vector like find its length or magnitude and create a unit vector in the direction of that vector by taking that position vector and dividing it by its length. Now, a displacement vector would be a vector created by displacing the endpoint of the position vector by a different differential amount dx, dy, and dz. So that is a new vector which we can talk about it representing the change in the original position vector. So differential calculus for vectors. Let's go over some basic calculus. If f of x is a function of one variable, then df dx tells us how fast f of x varies when x varies by a small amount dx. It's typically known as the slope of the tangent line to the curve of f of x in high school calculus. And the key takeaway for this is that if we change x by just a small amount dx, then f of x will change by the amount df. And the ratio df dx is the proportionality factor of those changes, typically known as the derivative. Now, derivatives in three dimensions. Let's talk about something like temperature, a scalar function. So at any point in a room, you could measure the temperature in that space. And now the derivative will depend on the direction you move. In other words, the temperature will change depending on your direction. Let's say in a room, if you are judging how the temperature is going to change and you move upward towards the ceiling, you'll notice that there'll be an increase in temperature because heat rises. But if I just walk from side to the room, not much temperature variation will be noticed. So how fast does the temperature change? Well, temperature is a scalar function. It doesn't necessarily have a direction. A theorem from partial differential equations states that the change in temperature dt can be given by a series of linear combinations of partial derivatives. And so we can visualize this linear combination is actually a dot product of vectors, one which is the gradient of the temperature, and the other one which is the displacement vector of the position vector r. So the first derivative that we come across in three-dimensional space is this generalized derivative called the gradient. Now, if we use the dot product formula that we're used to with vectors, but now with this particular dot product, we get an association with not only the magnitudes of these vectors, but also the direction angle between those two vectors. So, what does this expression tell us? If the angle happens to be 0 and those two vectors are parallel, going in the same direction, then the cosine is going to reach its maximum value of 1, and the change in temperature will then also be maximal along that direction. Now, if we notice, that happens when it's parallel, the gradient of a scalar valued function, or quantity, del t, uses a differential operator, which is the partial derivatives along the different directions x, y, z. And it itself is considered that to be like a vector. It behaves just like a vector. So this vector points in the direction of maximum increase of that scalar function, and a negative would just be simply a pointing in the direction of maximum decrease. The magnitude of this vector, or the magnitude of the gradient, gives the slope, or the rate of change, along this maximal direction. So what does it mean for the gradient to vanish, or equal 0? So at a particular xyz point, if the gradient happens to vanish, then the change in temperature here would also have to be 0. That is, there is no change in temperature. It's a stationary point for the temperature, something we might call a local extrema. That's similar to when you do the first derivative test, setting it equal to 0 to find relative extrema. So now we have this operator called del, or sometimes referred to as nabla. It's an upside down triangle, and it is the vector of partial derivatives. An operator acts on an object like a scalar or a vector. So consider two arbitrary vectors, a and b, and a scalar value, lowercase a. We can define three types of multiplication with vectors: scalar multiplication, dot product, and cross product. So similarly, we can investigate what those types of products would mean using this new del, or differential operator. Next is the divergence. So this is a dot product with the vector and the differential operator del. It'll produce a scalar number which will indicate something about the space at a particular point. If we consider a vector field, which is a vector associated to every point in space, and we can talk about how those change as we move through the space, then the divergence can tell us something about how those vectors would change in the vector field. So if the vectors don't change or remain constant in the field as we move, then the divergence will be indicated to be 0. There's no outward spread of the vectors. If there is an outward spread of vectors, it typically indicates something called a source, like a faucet producing more water at a point. Or, if in the same analogy, the divergence is negative, that's a sink, where the space is sort of draining out into that point. The curl, another type of multiplication with vectors, is a cross product of the differential operator and a vector. And this is done in the same way we do a cross product, through the determinant formed by the components of the differential operator, the vector components, and of course the basis vectors I, j, k. You might see different notation used. I'm using a shorthand curly d for the partial differential operations here, but finding the determinant of a matrix, you just take some careful time to do it right. You'll often make a mistake with a negative sign, as I do, and you won't get the right vector. Now, this is going to produce a vector that is, in theory, perpendicular to the differential operator as well as the vector v, and this is an indication of how much a vector curls around a particular point. Now, second derivatives, we can think about those as just applying the del operator a second time. So we have the gradient and the curl, those produce vectors, and a dot product of a vector like the divergence is a scalar value. So we can take the divergence and the curl of vectors, and we can take the gradient of a scalar. Those are the things that make sense. So we consider four possible combinations: the dot product of the gradient, the cross product of the gradient, the cross product of a cross product, and the gradient of the divergence. So just doing some operations along vectors here, we would find that the dot product, or the divergence of the gradient, is going to give us a second derivative scalar. We sometimes call this the Laplacian operator when you see the triangle squared or raised to the second power. We can explore the Laplacian of a vector. So that's going to produce another vector, actually, where the components are just simply the second partial derivatives of each of the components. A little bit different. The cross product, again, is just a determinant, this time with some differential components. And as you would expect, that we could write this out using the determinant rules. But because of symmetry on partial differentiation, we get a lot of things to cancel here, and we find that the curl of the gradient is always 0. So the Gradient of the divergence. Let's recall that the divergence is a linear combination or a scalar of the components of the vectors differentiated along their directions. So the gradient of this would be simply a vector of their second derivatives, partial derivatives. This is not the Laplacian. So we can consider one last possibility, and that would be the divergence of a curl. And the divergence of a curl will assign each component of the curl its own partial differential operation. And so when you first see what the curl is and then apply the dot product with the del operator, you're going to have some sort of distributive property here of the del operator, or the partial differential operators on each direction. So you see second derivatives popping out, and because of symmetry, many of them cancel to, well, you would imagine, all of them cancel here to 0. So the divergence of a curl is always 0. Hey, thanks for watching. Don't forget to hit that like, subscribe, and notification bell.